had the pleasure of meeting many people. Three of them are here, and we became friends. So there are Marc Tremblay, who is now Vice President of Microsoft. He was in Sun. And then Leon Alcalá, who was in Jet Propulsion Laboratory. He's retired, but I told him, you will never be retired. I said, you are right, Mateo. And Jaime Moreno, who is from Chile. So all the three were working with Tomás. Tomás was very, very good. He was animating you every day, but he was very strict. I mean, he was very serious. So these guys suffer a lot, but they enjoy a meeting with Tomás, no? Is that true? So thank you for coming to this celebration. I think that Alan, where is Alan? Alan is one of the two sons of Tomás. Okay, would you like to say something to the audience?
Muchas gracias.
Esta tarde será tu turno. En perfecto español hablarás.
Muchas gracias a todos. Thank you for being here and honoring him.
Español.
Gran honor. Y estos sufrieron mucho, como él dice.
Y otros muchos. Y Miguel Huguet y todo esto. Los veía a los pobres, yo me iba de juerga y ellos se quedaban allí toda la noche estudiando.
Mi ex decano está ahí atrás.
Sí.
Francisco Urieva.
Francisco, sí.
También sufrió con Tomás.
¿Tú también sufriste a Tomás? Yo no, yo disfruté de Tomás. Porque como yo era doctor, iba yo sí le iba al comedor de los profesores, estos no podían venir, pero bueno. So please, thank you, thank you for coming here.
Dr. Tomás Lang also left a significant academic legacy, having taught UCLA, also at the Universidad Politécnica de Catalunya, where he founded the Department of Computer Architecture and later at UC Irvine. His influential textbooks and his groundbreaking contribution to high-speed, low-power processor remain a key reference.
Your wonderful country. Spent 3 days in the high desert with my wife a few days ago, and it was truly wonderful. And now thrilled to be in Santiago and reconnect with my, not only colleagues, but great friends, Mateo, Leon, and Jaime, his lifelong friends. Tomás was very influential in my career as my advisor and taught me a lot of principles, and we'll talk some more about it in the afternoon, but the methodology that he taught us was super important. He's a great teacher, and I have a lot of content today. It's all about AI. I'm a lifelong, 50 minutes. I will respect that, maybe 45 minutes. I will share a lot of insight. Some of the material I have is 4 days old, so I'll bring you up to speed on what's going on in the world of AI. And one more part, thank you, Mateo, for the introduction. And a lot of what he said is true. When I was building microprocessors, we were borrowing a lot of ideas from the supercomputer guys, right? And then in AI is, accelerator is fairly young science. We're borrowing a lot of ideas from the CPU folks, and a lot of the ideas that Mateo did. Kilo processor, nobody thought we could do 1,000 instructions in flight. It was groundbreaking, and I'll talk about stuff today like you might remember split streaming and scout threading. These are all ideas that are recycled in the context of artificial intelligence. And this time, the end goal is superintelligence, and I think it's probably the most important thing that we've ever worked on. And the sums of money that are being invested is just incredible, right? Matteo compared it to the budget of Spain. The reason I'm here is that last year, and the reason I spent so much time on scaling laws and training and inference is last year, Microsoft spent $85 billion in CapEx, so basically building hardware. A few years ago, we'd probably spent 10, and this is bigger than what governments are spending. And if you add up, what Google spends and Meta and AWS and China and other governments, it's just incredible what's going on in our space. So quickly, the agenda, I'll go through what we call co-pilots very quickly, 2-3 slides. Microsoft's term for AI assistant. And then we'll talk about very deeply about the AI scaling laws. And then I'll go into generative inference, past and future speedups. And then finally, energy, the impact on energy. And this is all through the lens of a hardware person who has been doing hardware for decades. So first of all, very importantly, we see AI as a co-pilot. You are the pilot. The humans are the pilot. And AI is your assistant that helps you achieve more and run faster and code faster. Agents work on your behalf and so on. So, and the first one that came up was really GitHub Copilot. And the next slide covers it in more detail. But this was really the first time we came up with an application that we could actually charge money and that people would pay for, because it just made you more productive. It was a very easy argument to make. And then we leverage our assets, right? So the Edge browser, Bing. My first encounter, GitHub Copilot, was GPT 3.5. And by the way, if you use an OpenAI model, they've been 100% trained on the hardware that I help build and design and influence. If you use your Apple iPhone, your laptop, whatever device, and you run a ChatGPT query, it runs in Azure. So it either is an OpenAI model, it's a Microsoft AI model, or an open source model. A lot of them run on Azure. And then we leverage our assets. What happened in 2023 is we got exposed to GPT-4. Sam Altman came over, and we were just blown away. And we said, why don't we marry this with, or couple this with search, right? Because remember, the model was self-contained. It had no idea what was going on in the outside world. It was trained months prior and was not connected to the internet, really. So marrying search and the AI was the breakthrough for us. And then we introduced this to GPT-4. And then, of course, why would you want to ever learn how to do Excel macros, right? You should just use AI to program spreadsheet macros, right? So we're introducing this in all our, what we call first-party apps. And likewise, other very important stuff like security. Why not delegate security to AI? So we have security copilots. So just quickly on GitHub Copilot is an experiment that we ran. And you had like 95 people, half of them used Copilot, half of them did not. Well, we were talking to Alan about modern AI tools, finished the task in about twice as, half the time, with less bugs and more quality. So these are easy arguments to make, right? People make hundreds of thousands of dollars coding and say, hey, for $19 a month, you can be twice as effective. Very easy argument to make. Now, let me dive in very deeply into AI scaling laws, training, impact on model quality, and impact on hardware. This is critical because this is why we invest. If scaling laws exist, or we didn't believe in scaling laws, we wouldn't invest, we and the rest of the world. So in 2020, OpenAI published a paper saying that, so let's say I had 10 exaflop of compute, and then the Spanish government or the Chilean government gives me 100 exaflop, 10 times more compute. How should I dedicate this hardware? This said that you should dedicate the hardware 5x to, well, building a model that's 5 times bigger, and then 2x and feeding it twice as much data. That's how you should spend your 10x of more compute. And this is, as an example, GPT-3 was 170 billion parameters, and using this model was trained on 300 billion tokens. Don't have to remember all these numbers, just remember it was 1.7 token per parameter. It's kind of small, right? This has to contain all the knowledge and all the reasoning and only 1.7 token per parameter. So then came the Chinsella laws that looked at it a little bit differently and said, no. It would be better if you had 10x more compute, if 3.1x was dedicated to make the model bigger and 3.1x roughly to provide more data. So this got exploited to the extreme. If you look at Llama 1, 2, and 3, Llama 1 uses 142 tokens per parameter from 1.7. Llama 2 uses 284, and Llama 3 almost 2,000 tokens. So now we're training models much longer, feeding them a lot more data, and I'll spend a lot of time on data. So then how do you know you're on the right track? So this was another chart that was produced by OpenAI saying, we're about to spend $10 billion, let's say, on GPT-4. How do we know what we're going to get? And this was a projection of where things were going to be using 1,000 less hardware, but predicting through scaling law where this was going to happen in terms of whatever metrics on the vertical axis is, intelligence metrics. In this sense, was the pass rate, in this case, was the pass rate of executing some Python functions. So empirical prediction, and he ended up at the right place. So let me just ground everybody in terms of hardware. Matteo covered some of this. Here's the workhorse that was used for all the models that you hear about today, except for maybe Gemini, which was trained on GPU, but everybody else pretty much uses NVIDIA GPUs. So we have a GPU package. You see the die here. And these are the HBM memory stacks. So 6 HBM stacks, 80 gigabyte of memories, providing 3 terabytes per second. And the hero data type here is floating point 8. Matteo covered some of the data types. We'll revisit that a little bit. 700 watts. This is the workhorse. And then you put 8 of them in a system that's about this big. 2 Intel CPUs, and here's your system. You rack them, 4 of them, and it's called a rack. Okay, that's the fundamental component of what we built. So how many of these do we need to run these big models? So I'll spend probably 5 minutes on this slide. So people in the pre-deep learning era were inventing models and were dedicating twice as much hardware to training the model every 2 years. Basically Moore's law. You had a certain budget. 2 years later, I'm getting a hardware that's twice as fast, the same amount of money. I'm going to train a bigger model. Here comes 2012 with AlexNet and GPUs, and people are doubling the amount of hardware they dedicate to training a model every 5.6 months. And then in the LLM era, there's still 2x every 9 months. This chart, I put a couple more dots at 2022. Since 2022, it has accelerated. So back to our, and these are, teraflops, petaflops, exaflops, zettaflops, yottaflops, and after that is ronaflops. And so the one GPU we looked at was 2 petaflops, but let's say in training, not everything is FP8. Let's say you get a petaflop. So 1 GPU, you're up here. Let's put 100,000 GPUs to work. So 10 to the 5. So now we have 10 to the 20. So we have 100 exaflop in one data center. Flops is per second. So how many per day is about 100,000 seconds in one day. That's another 10 to the 5. So now we're 10 to the 25. So we're at 10 yottaflops of compute every day. So if you say, I want to train for 3 months, 100 days, multiply this 10 yottaflops by 100, so you have one run of flops to train a model. So then you derive what your model size should be, and that's it. So this is 100,000 GPUs has been done. Extrapolate this to 2025 and beyond. You start talking about millions. But how much do we need, right? You look at this and say, well, it's another way to look at where models have gone. The lower the better here. This is the log of perplexity. The size of the bubble is how much compute is dedicated to run a model. And you look at the orders of magnitude here. So there's 8 orders of magnitude in terms of model size in this chart. If you go horizontally for the same quality, bubbles get smaller. So you need less hardware to train a model that delivers the same quality from a few years ago. Another way to look at this, love this paper that says, where are the contributions coming from? Is it model quality? Is it algorithms and hardware? And the numbers, you know, are not all based on empirical analysis, but great analysis nonetheless. And the thing to remember here is that over 10 years, algorithms have delivered about 22,000 times better improvement. And hardware here is shown 17 million, but let's say roughly a million. The main contribution came from better hardware, and I'll mention data types and all that, but significant portions from better models and better algorithms. How much do we need? Here's just one view. Everybody has a different opinion on this. This is an MIT paper that said, well, if we want to be able to write a novel scientific paper of, let's say, 10 pages, their estimate, there are many estimates out there, is 10 to the 35 flops. That's 8 order magnitudes more than what I just talked about. How are we going to get there? We're certainly not going to spend 100 million times more money. So that's where we come in, that's where you guys come in, algorithms, hardware, and that will be basically the rest of my talk. How are we going to get there? So another way to look at this, GPT-2, think about a preschooler going to GPT-3, elementary schooler. We needed 2 orders of magnitude more compute. Another 3 orders of magnitude more compute. Yeah, GPT-4, kind of a smart high schooler. Now we're probably around here with GPT-5, and at some point we'll have really good researchers. So where are we today in the state of the art? This is running in our data centers today. So the terminology from NVIDIA is a little bit complicated. This is called a super chip. This is a CPU up here. One GPU package, another GPU package. You put these together, it's called a super chip. But notice here in this package is one die here, 800 square millimeter die, another one there. So this, for the first time from NVIDIA, there are 2 dies. 8 HBM channels and times 2. So now we're talking about more HBM, more bandwidth, significantly more bandwidth, 11 petaflops per GPU in FP4. And now the power has gone up. That's the unfortunate part, right? So in the compute standpoint, 5x more compute using FP4 as opposed to FP8. Matteo mentioned it for inference. We're starting to sit in training as well. Is becoming the hero data type. Bandwidth hasn't gone up as much, but if you multiply by 2, because now you're transferring FP4 numbers as opposed to FP8, virtually you're getting twice as much bandwidth, twice as much capacity. It is about 5.5x. So much better part, more compute, that certainly helps. Then instead of putting 8 GPUs in a system, put a rack of 72. Now Jensen is not that short. This is a blow up of what a rack looks like, but this is called GB300 and NVL72. A board here has 4 GPUs, 9 boards here, 18 boards, so 72 GPUs. What does that buy you, to have this much compute in a rack? So now the GPUs are connected to a very fast interconnect called NVLink. And Jaime actually will talk a little bit more about NVLink this afternoon. But what does that buy you to have 72 instead of 8 in a rack? Well, from a training perspective, there's significant performance improvement. I can't share what the number is, but because you're able to run larger matrices and communicate more rapidly, is an integer multiplier percentage of improvement versus having 9 systems of 8 GPUs. And from an availability perspective, there are 5,000 copper cables in a rack. Thank you for the copper to Chile. You can imagine with 5,000 cables that things don't always go right. Running at 900 gigabytes per second, things go wrong. So having more GPUs in a rack allows you to swap some around and move them around from an availability perspective. On the inference side, having 72 GPUs in a rack allows you to run a much larger model and apply all the different parallelism method, tensor parallelism, pipeline parallelism, expert parallelism. Have at it. They all run well because the GPUs are interconnect very quickly to very high-speed links. So what do we do with this rack? Put it in what we recently disclosed as the largest data center in the world. 127 hectares, 1.2 million square feet of floor space, and you can see it here for the first time, 2-story data centers. And these data centers, this one happens to be in Wisconsin, are replicated not only in the United States, but in other parts of the world. And they're connected to an AI WAN, so you can actually spread models across or distribute inference. And what is that? How much power is the question? I'll talk about power a little bit on. For sure, a lot of power. And also what we forget, we were discussing last night, we have memory now, right? You remember what you looked at 2 days ago, last week, with your consent, of course. So look at next to this data center, we have storage and CPUs, and this is the length of 5 football fields, just for CPUs and storage, in addition to the GPUs that are up here. So again, talking tens of billions of dollars just for a single data centers, and hundreds of megawatts for sure. So that helps, So we've got faster chips, more money, more power. Hopefully there's more than that, more science come in, right? So what are the other knobs that we can turn to get to this 8 orders of magnitude, or let's say 10 to the 35 flops for a model? So there was a seminal paper that says textbooks are all you need. It says instead of feeding a model all the junk that's on the internet, there's good stuff, but there's a lot of garbage as well. Just feed it textbooks, And this way, Microsoft built very small models called Phi that were way smaller, but same quality because they were fed quality textbooks. And then at some point, we started measuring as you shrink bits, are you starting to leave knowledge out, right? So the caveat with these small models is that they were not multilingual, they were not multimodal, they didn't understand pictures. So you sacrifice things and say focus on reasoning. And then as I mentioned, with RAG, Retrieval Augmented Generative, we added a search engine to the model, right? So then the model doesn't need to know all that knowledge. So what was the score of the football game last year? Who cares? We just use a search engine for that, right? So we started shrinking bits, getting 8 bits per parameter, and said going beyond 8 bits, we started losing knowledge. And we the approximation is 2 of the bits were used for knowledge, 6 of the bits were used for the reasoning in one of the publications. So here, say, hey, we have a search engine for knowledge, for reasoning. That's what we'll focus on. That's where we'll feed it better data. So you feed better data, you get better models. So it buys you some of that 8 orders of magnitude. Yes. Say that again? Yes. Very important. From a data perspective, you spend a lot of money licensing books, and content, and books that are 40 years old that nobody's reading anymore, that all of a sudden getting a kickback. But it's a huge topic. Where are we with data on that topic? So this, I'll just summarize it. You see in the upper portion is the amount of text that's human generated. But it's not growing that much, right? But you have some order of magnitudes in terms of token here. And this is how much we use for GPT-3. I mentioned 300 billion tokens. And on the log chart, right, it keeps increasing exponentially, how much is used. But pretty soon you reach the limit of what we have, right? And that's why when Elias Suskeller said, there's only one internet, so what are we going to do about that? Well, this is where synthetic data generation comes in. And hopefully this is supplemented with AI-generated data, or the data that we all generate. So when you use AI, just like you remember the original Google idea, and you clicked on a link, and you picked this link. The brilliant idea was to recycle this as a neural network. That a human said, that's the answer that I want. Same thing here. You have reinforcement learning through human feedback. Wherever you end up, that's great information. Well, AI, as we'll show later, is also exploring multiple paths and generating much better data so that we can have more data for our future models. So far, I've mostly talked about pre-training, training a large model for 3-4 months, football stadium size, multiple football size data centers. And that's where the scaling laws have focused. Fortunately, because this is an expensive proposition, there are 2 more scaling laws, post-training scaling and then test time scaling. And a few examples of post-training scaling is that, so let's say you're a financial firm, we run GPT-5 and say, I want to fine-tune it to my financial data. Well, we have a lot of companies that use Copilot, train in their own model. We train for months. You can train for days with much smaller data sets. And then your model is specialized in financial data. Distillation reminds me of TOMAS. This is when you have a big model training a small model. So you can spend a lot of money on a big model, but the teacher is teaching the student as a much smaller model that can run much cheaper and can learn from the big models. And this is something we actually have to protect ourselves against, because the big models available, for example, in the Western world can be exploited to teach models that are much smaller by perhaps countries that are not too friendly. Reinforcement learning, I mentioned reinforcement learning with human feedback. There's also reinforcement learning with AI feedback. For a few years, we had lots of people, human beings, that hired all over the world, just saying which one was the better answer, right? And that's not scalable. That's why AI has got to get back in the loop. And then finally, test time scaling was really the hot thing right now. Is at runtime, once you ask your question, how much time do we spend? How much compute do we spend on this? I'll spend a couple slides on that. Super hot topic. So post-training, I'll just show you in one chart, is that you could say, well, I can improve my model from 0.5 to 0.7 using whatever intelligence metric, spending 5 times more compute. So instead of having 1 data center, imagine having 5 data centers. A lot of money. Or I can spend time, this is not free, you know, the fine-tuning is not free, but I can spend some amount of compute post-training to get the same level. Super important. So just, we spend quite a bit for our IQ and budget on this. Perhaps more important is test time scaling. So you might have noticed how queries can take, 10 seconds, and if you use a Copilot researcher, it'll take 12 minutes, or deep research, same thing. And pretty soon we'll see things taking, a day, a week, and the kind of work I do, I couldn't care less if I wait 10 minutes. It accesses, if I use researcher, and it accesses all my emails, all my Word documents, all my Excel spreadsheets, all PowerPoints, all SharePoint sites that we have access to in Microsoft, and then the internet, all with my consent, and it doesn't have any more priorities than I have at the company. Then I asked to produce research reports, and it crunches for 12 minutes and comes back with an 8-page report. It's irreplaceable. So think about, I often bring it back to how humans reason. So the classic example that this guy described was, if you're playing poker and you're playing, 1,000 pesos at the beginning, you just don't do much thinking. You just bid and bid, bid. And then the pot gets bigger and bigger and bigger. And the pot is like several $1,000s, and say, I want to spend a little bit more time here. It's the same analogy here. So if you care more about the quality of the answer, we just spend more compute and more time. And chain of thought is just about breaking down the problem in multiple steps, generating the intermediate tokens, and feeding the model through that. Super hot, and we'll see how that translates into model quality. Majority voting, you have a team, same thing with search, you have a team exploring multiple paths, perhaps 20 different paths, and then some voting, which maybe 3 of them ended up with the same answers. That's probably the better answer. So spending time at test time or at inference time has been the rage. What's the hardware impact? Well, strangely enough, a lot of this is inference computation. So instead of having just a very homogeneous training data centers will have a lot of inference hardware as well. So we'll see much more heterogeneous architecture. So this paper talks about, if I have a certain budget of flops, should I spend, 10 times more on train time compute? So the gigantic data centers I showed you, should I spend 10 times more? If you do, it buys you inference time compute, but vice versa. So it's really depends how many customers you have to do doing inference and how much you want to dedicate or allocate for inference versus training. So that's kind of turning the knob today is super important, because look how much it's costing you or buying you. So here are normal models. On the vertical axis is another intelligence metric, very difficult, challenging AGI, artificial global intelligence benchmarks. You see the scores are pretty low here. With reasoning models, here I have O3 low, makes a huge step. And then you say, well, I can go spend way more hardware, 172 times more hardware. It'll buy me some, and I'm going 76 to 88%, and it'll take 13 minutes versus 1.3 minutes. So depending who pays, what your subscription is, how much time are you willing to wait, that's the big breakthrough, right? Right now we've been doing mostly, chats and waiting a few seconds to get an answer. Here we're talking 1.3 minutes, we're talking 13.3 minutes. If I have to referee a paper that Matteo sends me, I'll be happy to rely on a research assistant. I'll be happy to wait an hour if I don't have to review the paper. Right? If for a certain level of quality, everybody will be willing to wait. All right, enough about training, quality of models. Let's talk about generative inference. So, two major cases. One is online versus offline. So offline, think about, hey, I want to summarize all the Wikipedia pages. I want to look at all the pictures I have and classify them. And you don't care so much about how much time it takes or latency to first token. You care about doing this in a cheap way. Online, you have much stricter latencies, much harder problems. For example, Copilot probably can tolerate 100 milliseconds to first token, and then a throughput of 10 milliseconds in between tokens. So to define that a little better, let me move over here. So the prompt phase or pre-fill phase is when you submit your prompt that might have 100 tokens, 1,000 tokens, or millions of tokens. And the most important thing to remember here is that this is deterministic. If you send 100 tokens, we know precisely how long that's going to take. It's not based on the semantic of the query. So, and it's a very parallel program, very parallel challenge. So you can easily parallelize this over multiple GPUs, and you're building the KV cache, the famous KV tensors, and that takes you to time to first token, and then you finally start seeing an answer. So then the first token is produced, and the main challenge here is that this is a sequential process. Right? You generate the first token, and the next token depends on this token, plus all the KV cache that was built during the pre-fill phase. So this phase here is very dependent on memory bandwidth and memory latency. So strangely enough, heavy compute dependent here, every bandwidth compute dependent on the backside. And then the other tricks that we play, same thing with search, right? If everybody is asking for the football score from last night, you don't have to generate a search again. We just cache it, right? So there is such a thing as a KV cache. So if your query is the same as somebody who recently did the same query, and remember, there's your query, plus there's the system query that says, please be a professional model and respond in a polite way. So the system problem is always the same. So we match the prefix and retrieve that information instead of processing it and recalculating the prefill. Okay, so I think I've said most of what's here. Thing to remember, super important, is this is very flop based. The more flops you have, the quicker you'll go. And the bandwidth between GPUs doesn't need to be as high as in the decode phase. And we go in the decode phase, a token generation phase. As I mentioned, it's a sequential process, and it's very HBM memory dependent. If you measured how many flops are used in this stage, you could be in the single-digit percentage of peak flops. Spending the $30,000 per GPU here, and I'm only getting 7%, 5% of the total flops. So the secret is to batch, to pile on a whole bunch of requests together that exploit the same model, reuse the same weight, leverage the bandwidth. That has an impact. That impacts how big your KV cache is, but it's you can get more tokens per second per dollar in this way. Type of parallelism, very important, used for decode. I mentioned the NVL72 that gave you really good bandwidth across 72 GPUs. Well, you can do tensor splitting, which is very bandwidth intensive, but will help you reduce this time to first token. And then, if not, because you've seen models like DeepSeek, where the model was developed in China and then didn't have NVL72. All they had was 8-way GPU systems, and basically pipeline the model across multiple 8 GPU systems or across a much lower bandwidth link. Well, the great model is fantastic, but the time to first token is longer and the time between tokens is longer because there's not enough bandwidth, right? So that's the trade-off, but certainly great engineering. So from a hardware perspective, same principles that Tomás taught us, that Matteo discussed, and I'm sure my colleagues will talk about later. You always look at bottlenecks, and wherever you have things that are not fully leveraged, you try to exploit them, and in this case, spread the model across. And one of the key observation that was done is what I just mentioned, the computing is different in the pre-fill than the decode. So we published this paper a couple years ago, split-wise, and how to split inference into these two phases. And this is now what NVIDIA calls Dynamo. And main idea is that you process the prompt, the pre-fill phase, on a bunch of GPUs. It could be 4 GPUs, and then say, well, I'm going to dedicate 11 GPUs to the decode phase. It can be the same GPUs, it could be different GPUs. And as a matter of fact, NVIDIA just introduced the CPX processor that focuses on pre-fill. So here, do something that's fast for from a compute standpoint, do something that's very memory bandwidth efficient on the decode phase. Another idea, I mentioned split stream speculative decode that we've been doing for CPUs for a long time. Here the idea is you have a smaller model that runs ahead of the bigger model. The smaller model is cheap, can run ahead, and is mostly successful. And then all the big model has to do is the big model is you can batch. And the thing is, the key observation is running a batch of, let's say, 4 tokens, 4 queries. It takes about as much time as it takes for 1. So ganging 4 buys you almost a factor of 4x. So most inference system I know today are using speculative decoding. All right, so how did we achieve the 1000x speedups in the past, and how are we going to get there in the future? So this was a slide presented by Bill Daly at Hot Chips in 2023, showing that, well, number representation, it's interesting in the CPU world, right? We went from Intel 404, 4 bits to 8 bits. Here we're going the opposite way. We're going smaller and smaller. Complex instruction using, larger and larger systolic arrays, matmul instructions, vector instructions, provided, in his opinion, was 12.5x. I disagree with the fact that process only bought you 2.5x. I think that's more the transistor speed standpoint, but for God's sakes, we're getting area, we're getting cores, right? We jump from like 100 times more cores going from 28 nanometers to now down to 1.8 nanometers. So process certainly is buying us a lot more at a cost, and the power cost as well. Sparsity is still a debate, but can certainly buy you some. And model efficiency. So certainly over the years, incredible improvement. Matteo showed a slide on data types. I will share one more hot topic on this. So here's the exponent. Miloš and would probably love this, and Tomás as well. A sign bit and then the size of the mantissa. If you look at FP8, FP8 can have an exponent of 5 bits or 4 bits and a couple bits or 3 bits of mantissa. The idea that we came up at Microsoft was shared exponents. And you looked at the data and it says, all these data, 16 of them, kind of all have the same exponent. So why should I replicate the exponent 16 times? Well, I have the same exponent, in this case a beautiful 8-bit exponent, and I'm going to dedicate 5.5 bits per data. So in this case you have, let's say, 16 FP8 with a smaller exponent is 128 bits. Here you have 16 of MX6 data types. The exponent is not replicated, so 16 times 5.5, 96 basically, plus the 8-bit, 96 bits. So you have fewer bits and you have better quality. You have a larger exponent. So, and I'm showing this here, going from FP8, on the horizontal axis is how much area and power does the multiplier take, for instance, a multiplier and adder. So with MX6, you half the power, half the area, and quality goes up. This is signal to noise ratio. So every single GPU or AI accelerator, modern one today, uses this idea. We pushed it in the public domain. NVIDIA, AMD, we're doing in our own accelerators. The Maya line is using a shared exponent. And FP4 or NVFP4 is becoming the hero data type. Can we push it further? This was another paper that we published using 1.58 bits. So basically -1, 0, and 1. So log base 2 of 3 is 1.58. That's where it comes from. But think about 2 bits. And got very good results on this. And we're trying to demonstrate right now, does it scale to large models? At some point, you have the theory of information, or information theory, that says you keep compressing things, you're losing information. So you keep chopping bits, you keep making the models smaller. Something has got to give. So we're working on this, and if this works out, it kind of enables other technology like analog computing and perhaps optical processing to happen. How about using log numbers? What an old idea. So, well, adders are a lot cheaper than multipliers. So the idea here was to do the main computation in the log domain. And there's a company called Tensordyne that just showed this publicly. And great idea. The problem is to go back and forth between the decimal domain and log domain. And this mattered a little bit more when the data types were larger. Now we're getting down to 8 bits and 6 bits and 8 bits. The size of the multipliers and the shifters are not as big. But can I buy you a factor of 2? Probably. Analog computing is where, as I mentioned, if you go down to very few bits, you can do the whole multiplier and adder in the analog domain. There's no multiplier here. It's just like those lines, and using multiple levels of voltage, and it just gets added automatically. What about process technology? Showed going down to 2 nanometer. Matteo talked a little bit about this. So we're still getting benefit from process technology. Right? If you keep the power constant, ISO power, you can multiply your speed up to 1.6x, going from 7 nanometer to 2 nanometer. Of course, there's the density thing here. Or you keep the speed constant, you buy yourself power. Right? But unfortunately, the cost is higher, and so the price per transistor is not decreasing as rapidly as it has in the past, which is a fundamental component of Moore's law. I'll share one slide on process technology. This is what Intel has been working on and now finally shipping production chips. For those not familiar with what a chip looks like, believe it or not, transistors are only here at the bottom in this layer, and these are all freeways and roads, right? All interconnects, metal layers, and this is where we send power from the top all the way down to those transistors and taking a lot of area. Right? The idea from Intel was, why don't we go from the other side of the chip and bring backside power to those transistors and keep the interconnect then just for the important data bus and information that needs to be transmitted. So very cool idea. It's working, and finally seeing it in production. So Intel making really good progress on their process. Packaging, how much is that buying us? Well, we saw the NVIDIA Hopper 101 medical die here. Maximum die you can print is basically roughly 850 square millimeter. All the manufacturers are printing, manufacturing like 800 plus square millimeter dies. Here's one from AMD that has multiple dies and chiplets all looked up in the package. This chip from Intel had 47 chiplets in the package. Ponte Vecchio was used for supercomputers. And NVIDIA Rubin Ultra, you see one die here, another one here, another one here. So it's starting to we're building bigger and bigger packages. Unfortunately, these packages are bigger and more expensive and also burn, roughly here 4 times more power than having a single die. So what do we do about the heat? Well, the best heat conductor is diamonds. That's not what my wife thought. So believe it or not, people working on synthetic diamonds just to put under those dyes to spread the heat and take the heat out. And that's something that my friend Leon will talk about, I'm sure, later on. Leon last night handed me, this pocket and the other pocket, hands me like $6,000, he thought, but it was 6,000 pesos. He says, Mark, only talk about things that happen on Earth. Don't talk about space. And I will respect the deal even though it's only 6,000 pesos. So, yeah, basically. Liquid cooling, nothing's happening right now without liquid cooling. So this is the chip that we built at Microsoft Maya. And you see how we're sending liquid and cold plates directly on the die to cool it off. And it'll be interesting. Well, I'm sure we'll get into hearing some good stuff from Leon on that. And you see the rack on the right has all liquid cooling here, and then this is chill with these fans on the other side, on the other part of the rack. So this doesn't need water to come from inside the data center and rejecting warm water, what we call facility water, into the environment. This is all self-contained, which is kind of the plus. The negative is that it does take space and it does take power to run those fans. So people are starting to talk about putting a cluster of 400 kilowatts, like I'm showing on the top here, in a single rack, much higher density racks, up to 400 kilowatts per rack. What about optical computing? This was in science and technology. I was an undergrad student and I was already working on doing fast Fourier transforms with lasers. And it's an old idea, but I think it's an idea whose time has come. So there's a lot of startups pushing this right now. And Microsoft just published a paper in Nature talking about using optics to do matrix vector. And 3D optics in this case, and this is basically consumer electronics. Think about this as a little LCD display or projector, and each pixel here represents a parameter. And you're shooting lasers at this as a vector. It's fanned out to this, composed with that, fanned in, and that's how you compute a vector matrix computation at the, pretty much the speed of light. Pretty phenomenal. As you can imagine, you couldn't do this at high resolution, like 32 bits, 16 bits, but the more we go down in the number of bits, the more this technology becomes realistic. What about energy? The gentleman here asked me about power, so did Jaime, my former best friend. So we made a commitment to be carbon neutral by 2030, And obviously, we're spending a lot, on power and with our data centers, and to be water positive by 2030. So we're making all kinds of investments in fusions and fission. I never thought I would mention nuclear fusion in the same sentence as artificial global intelligence. But here's a company I toured, visited, and we invested in it, called Helion, and it's just north of Seattle. And believe it or not, we're taking delivery of their first generator in 2028. It's only 3 years from now. Well, maybe they'll be a year late, but certainly from now till perhaps the early 30s, I think fusion's going to happen. And fusion is a bit of a panacea because it also solves the water problem, right? And the key idea here is that instead of all these nuclear reactors basically boiling water and generating electricity, this uses the reversed Faraday effect, and the electricity is recaptured by capacitance, and we can leverage the power. And the big question will be, do you put this on the grid, or do you connect it in a closed loop with your own data center? So probably 50 different entities working on this worldwide. There'll be multiple winners, and it's hard to get around without energy, so I'm very optimistic on the impact this will have on society. And this was another one, Commonwealth fusion system I visited in the Boston area, using the tokamak idea. Lots of companies investing in this. So very promising. I think we need it. This is safe. It's been around the corner for 75 years, since the first hydrogen bomb was detonated. But it seems like it's coming, and we're investing this way, and we're investing along with Bill Gates in the smaller fission reactors as well that are a lot more safe. Okay, so no plateau in terms of intelligence as far as I can tell. The scaling laws help us predict and keep us confident. The path to global intelligence or super intelligence is super exciting. I couldn't be more excited to work on stuff like that. We have to be responsible. We have to be careful, because these systems will produce phenomenal stuff. And can't wait to share more during the break or over lunch. And thank you very much.